this talk. I want to speak about instabilities in spherical systems, radial orbit, and loose cone. And sorry. Yeah. And I will start with introductory movie. This is embodied simulations of radial orbit instability, which we made with Peter Bercek several years ago. On the left, you can see spherical harmonics, which we use to analyze angular redistribution of matter. And L equal 1 is simply mass, which is conserved in the simulations. And L equal 2 is a quadrupole spherical harmonics, which is nearly zero at the beginning. And then it starts to evolve. You can see this exponential growth and saturation and oscillation in some level. So our theory focus on this part, lower amplitude part, and we can calculate from theory characteristics of the behavior of low amplitude evolution, such as growth rates, for example, from calculating eigenmodes. So instead of historical overview, I suggest this timeline, which starts from Antonov's papers, who basically proved stability of isotropic systems. So from this moment, we are interested only in anisotropic systems. Mikhailovsky and others proved stability of Einstein's sphere in harmonic potential. My father, Valery Polychenko, and Ilya Shukhman first noted that radially anisotropic systems can be unstable. And then Antonov proved it for purely radial motion. Then in 1981, two big steps forward were made by starting embodied simulations and calculating of eigenmodes in spherical systems, which resulted in so-called Russian stability criterion. And then publication of Friedman and Polychenko's 2 volumes book, which raised interest in this subject in the West. So these works, these are embodied simulation works, these are theoretical works, so different kind of works. This one is 1991 paper, first notion about loose cone instability in disks. And of course, this 2005 paper on loose cone instability by Scott Tremaine. And this one, the paper in which we suggest a new linear matrix method, which we use this through this past decade. And I will, in my talk, I will resume the results which cover obtained during this past decade, which basically cover these topics: radial orbit instability, properties, and I will argue that the term radial orbit is not very appropriate. It doesn't cover full details, all details of the phenomena. And also, I will speak about loose cone instability, its properties, and I will show you embodied simulation. So, first of all, I will remind you the stability criterion. It is an empirical stability criterion based on a solution of using matrix method, like Kalnice, but for the spherical systems, for several models. And the idea was to establish a stability criterion in terms of global parameters, similar to Stryker and Peebles for disks. And the global parameters were total kinetic energy in radial and transverse direction. So when this ratio becomes is larger than 1.7 or plus minus something, the system should be unstable. But experience have shown that the hope for this such kind of stability criterion with this narrow range is groundless. First, Barnes et al. Shifted the initial range to 1.4 for generalized polytropes, and then Palmer and Pampaloiso shifted to the isotropic limit. On the other hand, Metze and Zamarana obtained stable system for 2.5, and Trenti and Berti obtained Osipkov merit for 2.9. So unfortunately, there is no stability criterion in terms of these global parameters.
You have plus 0.5 or whatever, the plus minus, what does it mean?
It was uncertainty. They was uncertain about what is exactly the boundary. So what is the mechanism for instability? Initially, Polichenko and Schuchman assumed that it is a kind of Jeans instability in the anisotropic media when velocity dispersion in transverse direction cannot resist gravitational attraction. And this point of view was shared by this minority. The majority prefers so-called orbital paradigm, which goes back to Lynden-Bell 79 paper. And these plots I have shown an orbit which moves with uniformly in spherical is in symmetric potential, and this one moves in the potential with the vertically oriented bar. So it is accelerated to the bar and can be captured by the bar, and this is essentially Lynden-Bell mechanism of bar formation. And the very term radial orbit instability comes first from Merite-Aguilar and Aguilar paper. So in orbital paradigm, you have to average over motion of a particle over the orbit. So you come up with a precessing orbit, and depending on the potential, these orbits can be prograde, so they precess in the same direction as the particle rotates, retrograde, or they can be donkey, as Donald Lynden-Bell calls them, meaning that they slow down when they pull it forward towards a perturbation. So they behave like a donkey. And the necessary condition for radial orbit instability is positive precession, and another one is that they accelerate towards the bar perturbation. In theory, we have a full matrix equation. I have only one but big formula, and here you can see there is a double sum over this frequency combinations, and the orbital approach uses several simplifications, one of which is a distribution function should peak at a low angular momentum, and since you don't have any other frequencies except precession frequency, you physically assume that frequency of the perturbation is of the order of this frequency. So then you can retain in this equation only these terms and come up with this slow matrix equation. But I will show you examples of fully self-gravitating systems that there is no reason to consider that this frequency is of the order of the precession frequency, and which means that you have to solve always full equations, except there is a explicit slow parameter of the problem, which is, of course, dominating harmonic or Keplerian potential. This is a small parameter. M is the mass of the cluster, and M star is a black hole mass or enclosed mass of the halo. So on this slide, I want to show you how eccentric radial orbits could be in the instability. So I use softened polytropes. This looks like generalized polytropes, but instead of power law for angular momentum dependence, I use Heaviside function here. So I have this diagram of an isotropy parameter beta. Beta equal to 1 stands for the purely radial motion. Beta equal to 0 gives isotropic models here. And what I'm going to do is to fix Q and go along the vertical axis and to see when radial orbit instability disappears. So for Q equal to 0, it will be here. For Q equal to -1, it will be here. And I calculated the trajectory for this L. It looks like this. So it's not quite eccentric. Hmm? Q is here. It's a parameter. So now let's go to the pure radial limit. Is this orbital picture adequate in this limit? We need to average over motion over orbit, and this implies that both real part of the frequency and imaginary part of the frequency is much less than radial frequency, omega 1. And what we have from our theory, we see that when we go to the purely radial limit, LT goes to 0, growth rate goes to infinity. So other way around. Enormous growth rates. Besides, we see odd spherical harmonics, which is impossible to construct when you have only symmetric orbits. And the orbital approach predicts that the growth rate is proportional to the square root of this quantity, which approximately true on this end, but not on this end. And we infer that for Q equal to 1, this orbital approach is invalid, and the same for Q equal to -1. One more example, Q equal to 0. Here's again a plot, a stability plot, parameter LT. This is a growth rate, and this green is a radial frequency variation for each model. So, and here we have several blue lines, which stands for the quadrupole harmonic growth rates. There are several, and we see that the maximum growth rates are much smaller. It is in the log scale, much smaller than the maximum of the radial frequency. And this one thing, and another thing is that we have only even harmonics, so there's no odd harmonics, and it seems that orbital approach is valid for this case. And also we see here black stars, which show consistency with n-body simulations. Finishing with this fully self-gravitating systems, I want to emphasize that sometimes orbital approach is valid, sometimes it's not, but you never know. So it's better to use full equation, so not sticking to the orbital approach. Now I want to go to the problems with small parameters, and I will consider neo-Keplerian systems first. So in these systems, for spheres, you have always retrograde precession, which means that it stables for radial orbit instability. Is there any other instability? We suspect that yes, using analogy with plasma physics, where This is a simple mirror plasma trap. Plasma which can escape in these directions, which leads to modification of initially Maxwell distribution function in this way. So you have a loss cone, and this loss cone produces loss cone instability, which leads in turn to increased loss cone filling rate. In gravity, such distribution functions can be obtained, of course, by tidal disruptions like this. So, and retrograde precession is welcome for the loss cone instability, and it seems that it is a requirement for this instability. Now, what is it really possible? Loss cone instability. Scott Tremaine in 2005 proved that dipole harmonics are stable, and it seems that quadrupole harmonics are also stable. We gave an example that octupole and high harmonics can be unstable, but this require non-monotonic angular momentum distributions. It is not a sufficient criteria, so we have a stability criterion in this case, but I don't have enough time to go into details. Nearly Keplerian systems is one example, limiting example of slow circular motion, and another example is a system within massive halos. So here I have a toy example, toy model of the stellar cluster with this distribution function. Delta means the Dirac delta function, and F, I assume here that F is simply power law. It's dependence on angular momentum. Here we have different profiles for different indexes, and as you increase the index, you eventually come up with retrograde orbits for n equal to 0.4, and you can see that it is exactly this point when instability occurs, loss cone instability. So, for example, for n equal to 2, we have an isotropy parameter equal to -1, which means that it is an example of unstable system with tangential anisotropy. And we made embodied simulation of this model with Peter Berzak again. So it looks like this, very unusual. This is because we have two time scales there. One time scale is due to harmonic potential, and another one is due to circular evolution. So another one is a slow one. So it looks like this. And you see, unlike radial orbit instability, it almost preserves its shape. And what we have from spherical harmonic analysis, this is comparison with the theory. So this dash dot line indicates the exponential growth rate, which is predicted from theory. It is consistent, but you see that it's saturated on a low level. And if we calculate other spherical harmonics, we see approximately the same amplitudes. So this explains why it is almost spherically symmetric. And here's the reason why it happens. This is energy, and this is angular momentum of initial distribution in the phase space. It looks like a line, simply a line. And then, as the system evolves, these orbits start to diffuse in this phase space. And this diffusion is turn out to be very fast. this diffusion leads to the fill of the loss cone, and then instability disappears. And here we compare the diffusion rate, which we measure as the mean square change of energy for this unstable mode, alpha squared, and compare it with another model, which we expect to be stable, 1 minus alpha squared. So I have plotted this quantity, which is expected to change with time linearly, but you can see that it doesn't change linearly, but this is square feet, so it changed like t squared. And here, this green line shows this stable model, the same quantity for this stable model. And we can magnify. We will see that it has linear behavior, and the diffusion coefficient maybe it is several times greater than what would we expect from usual two-body relaxation, but it is of the order of this value. So it is this what we would expect from conventional theory. So my summary: orbital paradigm is restrictive. We prefer Jeans instability in isotropic systems, as that it is more general. There's no simple stability criterion, and eigenmodes calculations require the full matrix equation unless there is a dominating potential. I gave you an example of unstable tangential anisotropic model. Loss cone instability in near Keplerian potential may give rise to higher harmonics, starting from octopole, but it seemingly requires non-monotonic angular momentum distribution. And loss cone instability affects the diffusion rate rather than the shape. Thank you very much for watching.